Welcome. Previously in this series we have looked at meshing, materials and sections between Abaqus CAE and 3D Experience. In this video we're going to take a look at steps. So let's get started. In Abaqus CAE we can change to the step module. An initial step is already predefined in the model for any initialization requirements. Then we can create a new step, define where it will go in the sequence, and what procedure it will be. Here for this lap joint, our analysis is going to be a 2.5mm pull of the top plate. We have nonlinear materials and will define contact between the components, so we will use a general static step for this analysis. We will provide an appropriate description, make sure nonlinear geometry is on. In a static analysis, time has no significance, it is instead just a counter. Often this is used to distinguish loading steps, e.g. step 1, 2, 3, etc. However, because it has no physical significance in the analysis, we can set it to be any kind of counter. Here we will choose the step time to be the same as the applied displacement. That way, while monitoring the analysis, we will know exactly how much displacement has been applied if the analysis fails or has numerical difficulties, etc. For the increments within the step, we will use an initial increment size of 1/20th of the overall step, keep the minimum for any cutbacks, and set the maximum to 1/5 of the step. We'll also activate the unsymmetric matrix storage. This adds the step to the tree. We can also see that this adds two default output requests. One for the default field outputs at each increment, and another for the default history outputs for the model. In 3D Experience, we've already seen that we have been introduced to the concepts of FEMs to organize mesh and property data. When it comes to simulations, we also have a concept of physics simulations. To create one of these, we will use a scenario creation app. Exactly which one you will use will depend upon your role. Here I will use mechanical scenario creation. You may also see structural scenario creation. When this app is chosen, if a physics simulation isn't already active, it will prompt to create a new one. So we will give that an appropriate name, and this will open in a new tab. Initialization will determine what type of physics simulation this will be. For mechanical scenario, this will be a structural, thermal, or thermal structural analysis. It will also prompt for an analysis case name. Here we will call this pull tests. This analysis case will contain all the pull tests we wish to apply. Finally, the analysis case needs to know which FEM to use. Here we created two. The one we will use in this example is the mesh of assembly, so we select that. Now, we've just introduced several new terms. Let's look at what happened in a bit more detail. The first thing to note in the tree is that there are three branches under the physics simulation: model, scenario, and results. This is how each physics simulation is organized. The model branch has the assembly or part that was pre-selected when the physics simulation was created. Alternatively, for a blank simulation, this would be searched and added to the model branch. In this case, the lap joint assembly was selected, so we see that in the model as well as the associated FEMs, sub-assemblies, and parts. Apart from this being in a model branch, this works just like the app joint assembly feature tree we've worked in the past. You could use this version to go in and edit the mesh, for instance, by expanding the appropriate branch. Since this does contain the geometry in the FEMs, this is the model information for the simulation. The scenario branch is where the simulation setup is stored. This branch uses the concept of analysis cases to differentiate between different analyses within the same physics simulation. An analysis case contains its own set of steps, initial conditions, loads, boundary conditions, etc. Here we made an analysis case for pull tests. There could be another analysis case for a drop test, or for a twisting load, etc. At the moment there is nothing within the pull test analysis case, but this will be where that data structure will be populated with the analysis options. Finally, there is the result branch. This is where settings and options for results post-processing will reside. Again, since no simulation has been done yet, this is an empty container. Users can switch between these branches by double-clicking on them, which will open different apps depending on what is being opened. In addition, on the action bar, we can see at the left commands to switch to apps for model, scenario, or results. It's not a direct equivalence, but generally we can think of the physics simulation as being like an Abaqus CAE model. If you opened an Abaqus CAE model, it would contain everything an analyst needed for doing that analysis. Similarly, if you open a physics simulation from a search on the platform, it will contain everything needed for that simulation. Towards the bottom of the screen, we can see a flyout which has a green tick for the pull test analysis case. This indicates that an analysis case exists and has been linked to use a particular FEM. There is also a red exclamation saying no procedures exist, which indicates that we need to set up the step definition. Changing to the Procedures tab, we see all the procedures that we could add. Here, just like in Abaqus CAE, we will use a static step, give it an appropriate name, and then we see the same options we had before for the step size and incrementation. Note, in this specific recording there was a mistake with 0.05 maximum time increment instead of 0.5. That was later corrected off screen. Under the Advanced section, we can see that geometric nonlinearities are on by default, and that we can choose the unsymmetric matrix storage so that we have the same settings between 3D Experience and Abaqus CAE. Expanding the pull test analysis case branch, we can see the pull 2.5mm static step, as well as two default output requests that have been created. These are the default options for field outputs and the default for history outputs. So in this video we've seen that the concepts from Abaqus CAE do carry over into 3D Experience. There is an extra layer with the physics simulation as well as the model, scenario and results branches. In addition, the analysis case is a way of grouping a particular analysis setup within the scenario. Analysis cases are not directly equivalent to Abaqus CAE. However, in practice they are conceptually similar to jobs and models, in that you can have multiple of them within a physics simulation and they keep that simulation data together. There are new concepts and slightly different ways of working, but Abaqus CAE knowledge can help when working on the platform. Thank you for your attention.